Hi everyone, it is February 19th, 2021. That means yesterday was the successful landing of Perseverance on Mars. Um, and we actually didn't know that it landed till like 11 or 20 minutes after it actually landed just because of the way the orbits work. So today, for our EMAC tutorial, we're going to look at Orbitize, which is a package for orbit fitting of directly imaged objects. Basically, what this does is it predicts future orbits with limited data sets. So, one thing that a lot of people may not know about submitting your resource to EMAC is we accept HTML. So here in their description, they say extensive tutorials are available here. So let's click here. And this will take us to this page where we can, learn how to install it and all that good stuff. We're going to go to the quick start. As y'all can see, it's purple because I've already been there. And yeah, so I took the liberty to make a notebook with all of that stuff over here. And we're just going to go through it real quick, and I'll kind of show y'all how to use Orbitize in the simplest way, and we'll kind of go in depth into what it does. So first, what you'll need to install, you'll need to make sure you have Xcode installed, and you'll need to have a Python upgraded, and it may ask you for BS4. That's why I have this pip install BS4, and of course pip install Orbitize. Other packages you might need include all of these. So just, if you're having problems running Orbitize, make sure you have all of these packages installed before you continue. So import Orbitize, and then we are going to create this path to file, and this file right here, this gj504.csv, it comes with the Orbitize package, so it'll automatically be downloaded when you download Orbitize. Orbitize has a file reader, and this is how to use it. This is the file that we just read in. This is what it looks like. As y'all can see, we have our epoch, our object, this quant1 error, quant2 error, and this quantity type. And all these quantities will depend on the quant type. So you can see here we have this SEPA, meaning separation. This is our quantity type. And because it is SEPA, this quant1 will correspond to the separation in milliarseconds. Quant1 error will be the error in that separation. Quant2 will be the position angle. Quant2 error will be the error in that position angle. And yeah, you can also use RAD-DEC, which is rate ascension and declination, and also RV, which corresponds to radial velocity. And you can't just import any old .csv file. It has to be compatible with this astropy.io.ascii.read format. So down here, you can also find this right here on this page. Down here, I made a note for us. So the rate ascension and declination are in milliarc seconds, and for those column names, you would be using RAOF. So rate ascension offset, RAOF error, decoff, so declination offset, decoff error. For separation, we just went through this. And for radial velocity, your columns would be radial velocity and radial velocity error. In addition to that, your epoch must be in MJD. If it thinks that it's in JD, it will attempt to convert to MJD automatically. If you want to double check that the conversion is being done right, you can go to EMAC and you can look up this buried core pi. And that is what we went over in our last tutorial. And buried core pi is this precise barycentric correction for stellar and radial velocities and timestamps, which does the same thing. So you can also mix and match the object formats as long as you keep them separated by object number. So for example, right here, if you have one radial velocity measurement of a star and 3 astrometric measurements of an orbiting planet, you should put the 0 in the object column for the radial velocity point and the 1 in the columns for the astrometric measurements. So what that means is, say for example, this first epoch was the star, this object would be a 0. This quant type would correspond to a radial velocity measurement, and then all these quant 1 and 2 and quant 1 and 2 errors, instead of them being in separation milliarc seconds and position angle, they would be in radial velocity and radial velocity error. So yeah, pretty convenient. This is an example of what a valid.csv input file would look like, and this is what it looks like as an AstroPy table. So now let's see how we create our orbits. And I know you're already seeing these warnings. Relax, it'll be okay. So what do we have here? So we import a driver from Orbitize, and driver will allow us to put in all of our data into one variable, if you will. So we read this in, we read in our file, which we already did above, but it's okay, we did it again. And we're going to choose between OFTI and MCMC. So OFTI is orbits for the impatient, and it's an algorithm that effectively predicts the next orbit, and MCMC is a Markov chain Monte Carlo. So we want to look at orbits, so we're going to go with OFTI, and we are just going to put in the number of the planets in the system. So in this system, GJ504, we're looking at GJ504b, so that'll be one planet, the total mass, and the system parallax, the mass error, and the parallax error. And then we're going to set orbits equal to mydriver.sampler.runSampler. So this is saying we want you to predict 10,000 orbits. Now we're going to plot the results, and all we do is just set my results to mydriver.sampler.results, orbit figure equal to myresults.plot orbits. The plot orbits is the module that actually creates the orbits, or that plots the orbits. And you're going to say, I want to start from the very first epoch. So start MJD from the first epoch. Now, all of these warnings, this is correct. This is predicted. Basically, we only gave it 7 orbits. So because it's predicting orbits so far into the future, it thinks that we might be in Julian dates as opposed to MJD. And it's telling us, hey, we ran this, but just so you know, you might have the wrong dates, even though we don't. We know we have the correct dates. And this is our orbits. As you can see, it created a plot of many predicted orbits. And yeah, it's really cool. So what just happened, Orbitize predicted about 10,000 orbits given a 7x8 data set, which is pretty amazing. So let's break this down a little bit, and let's see the statistical significance of these orbits. So now what we're going to do is we'll do the same up top. We're going to read in this file. We are going to create all these orbits. So again, this is the same line from above, and we want to see what one of those orbits looks like. So orbits 1 is equal to this s.runSampler. Remember, this is saying create 10,000 orbits, and this is the very first array, or the very first orbit. And in this array, there's 8 arguments, and this is what those arguments correspond to. So the first one, this 4.8, would be the semi-major axis. The next one, 8.1, would be eccentricity, and so on. And you can see this list below to see what they all correspond to. And yeah, this is just useful information. So now let's create a histogram. Let's say we want to make a histogram for eccentricity, inclination, and semi-major axis. All we will do, we will pull out these parameters from our param index. So that's up above. And you can just pull them out by name. And then you're going to simply do a plt.hist on all of these different parameters, and you can make a histogram. Pretty simple. So looking at it, looks like our semi-major axis stayed pretty consistent, which is what you would expect. And then our eccentricity and our inclination angle, those changed quite a bit. And that makes sense when you look at this plot up above. So cool. Now for a corner plot. So most of us, or most of you, or if you've ever worked with corner plots or MCMCs, you know it's a hassle and a half. This makes it super easy. And this is all you have to do. 2 lines, that's it. So first, so myresults.s.results. So remember, this .s contains everything we'll need, and the results will contain everything we'll need to make a corner plot. So all you do is you're going to set corner figure equal to my results dot plot corner. This is the param list. So again, pulling all of these out by name, and then you just you plot. That's it. And here is our corner plot. Now I know that it doesn't look like there's much convergence. That's okay. Again, this is predicted. You can see here that they'll tell you that you should probably go with like 1,000,000 orbits to get a nice clean corner plot for whatever paper you want to publish. So back to the original task at hand, which was creating the orbits. After we created the histogram and the corner plot, we'll just make the same orbit again, just as a quick little reminder. Remember, this is okay, this happens. And there is our orbit again. So what we did just now was we went through the quick start, and it was really simple. This is basically it. This is the only cell we have to use for the quick start. It says import this data set. It has to be specific in a specific format for Orbitize to use. Put in all these parameters. Tell me how many orbits I want to create. That's what this is doing. And then go ahead and plot that. So yeah, that's Orbitize, guys. If you guys have any questions, hit us up on Twitter, or you can comment below as well. And yeah, happy exploring. Peace out.